In this section, we're going to take a look at deep models with MxNet and TensorFlow, two different frameworks in order to build deep learning models. We'll look at working with MxNet and Gluon, which is a higher level framework on top of MxNet, defining and training neural networks in MxNet and Gluon, and then work with TensorFlow and Keras, which Keras is a higher level network on top of TensorFlow, and then define and train neural networks in Keras and TensorFlow. Finally, we'll compare the two frameworks and use what we've learned to build a mini project of training an AlexNet and Cipher network in order to compare the two frameworks, but on a classic set of problems in image recognition. Now in this specific video, we'll be looking at working with MxNet and Gluon. First by looking at what is MxNet, and then some of its fundamental data types, the ND or n-dimensional array, and symbol for symbolic math. Then we'll take a look at Gluon, which is a higher level wrapper on top of MxNet, and then we'll be revisiting logistic regression by implementing it with Gluon. So what is MxNet? Well, it's a library for math and deep learning with both imperative, meaning looping in code, and symbolic, meaning declarative interfaces. Automatic differentiation so that it can compute gradients, predefined layers, GPU, and distributed computation support are all built in. This is a full-featured library that you can do a wide array of mathematical, symbolic, and neural network computing. So let's take a look at MxNet in some code. The fundamental data type here is the ND array, or the n-dimensional array, otherwise known as a tensor. If you're familiar with NumPy at all, this has a similar API and can almost one-for-one be converted back and forth from NumPy. The main advantage of MxNet over NumPy shows up when we are doing deep learning though, GPUs and automatic differentiation support. So here we've created an empty array and it just has random values and it basically picked up what was left over in RAM. But you can also do normal matrix math, like we can actually set up two sets of ones and add them to build twos, or we can actually add a constant across an array and it broadcasts. We can also take an array and pick out a row, or do strides and slices to pick out individual values of the array right here. Going back and forth to NumPy is pretty easy. You actually say as NumPy, and then you can actually use a NumPy array as an input in MxNet in order to create values as well. Let's take a look at some symbolic math. This is more like the algebra you learned in school where you can encode a formula and the variables take on different values as it runs. Symbolic math allows MxNet to know your code as a formula and then give specific values, then compute gradients, and this can be used to create a raw interface to do neural networks. But don't worry, Gluon can take care of most of this for you. We'll start off with two variables, a and b, and then we'll build up a formula where 2 times a plus b, kind of a simple thing you'd remember from algebra in high school. Now we can bind those variables. We actually think of this as a function call in regular programming. By binding, we're actually passing in actual values into a and b. So we're putting a 3 in a and a 2 in b. And then we'll run the network forward, and you get an output value. Okay, that's pretty mathy, and I promised you wouldn't need a whole lot of math in order to work with MxNet and Gluon. So next we're going to take a look at Gluon and layer higher level interface. Alright, so what's Gluon? So you have your deep network you're building, and you build that on top of Gluon, which is built on top of MxNet. So the primitive operations we saw working with ND arrays or symbols are actually used inside of Gluon for you, and you can focus on a much more declarative and straightforward way of building your neural networks. We had previously looked at logistic regression, so now let's revisit logistic regression by building a network on top of Gluon on top of MxNet. Here we're importing Gluon, and we're going to use sklearn to get some data sets. We'll use our good old friends, the MNIST digits, which are available, and as a general rule, this is a great place to start when you're working with a new framework, because MNIST digits are well understood. You can think of them as hello world. That's the best sample program. So our transform here is a little bit different than what we learned in Keras before. We have to provide a specific transform function. The same kind of math is going on though. We're actually dividing by 255 to get the max, and then we're getting the label. So MxNet has these data loaders, and you actually pass it a data set, the MNIST, and then you use the transform in order to turn it into the final values you want. This is fairly cookbook code you'll work on over and over again. So let's take a look at some of these images and labels. We're going to iterate through the training data set and see the shapes. We see we have 32 in the batch with a 28 by 28 in one channel image and 32 labels. And now we can start making a network. We'll start off with 10 classes of output because we have the 10 digits to predict and make a dense network. And we have to explicitly initialize these with the normal. We'll talk about initialization a little bit later on, but basically it fills it in with a bunch of random values that we'll start for our learning. Now we have loss function, the softmax cross entropy loss, and we're building a trainer, the stochastic gradient descent with learning rate. So this is our loss function and trainer cookbook we talked about before. Now a little bit different than from Keras, we actually have to build our evaluation of accuracy. So we make an accuracy metric And what we're doing here is we're actually looping through all the data. We run our network, and then we take our softmax class values and run argmax to come out with the actual predicted class value and return and get that. So we get a sense of accuracy as the model by using this function to give us a percentage score of how accurate we are. And so here's our actual training loop. For the number of epochs, which is the outer loop, we run our network, recording the gradients and computing the loss each time. With these recorded gradients, we then run the loss backward, and this is what gives us the gradients and drives the deep learning step. And then notice the softmax cross entropy. We don't need to explicitly convert to one hot with MxNet. It actually happens under the hood for us automatically, so it's a little bit different than Keras. So we can work directly with the ordinal integer class labels. And this is the loop each time. You actually step forward by the batch size and then compute the loss and update the network. So you can see this is actually different from Keras that we saw before, and that it's a little bit more explicit that you have to run your own training loop. And you can see the loss come down and the accuracy run up. So that's Gluon. We'll actually learn how to make more powerful networks in subsequent videos, but for now, remember we didn't really have to specify some of the things we did in Keras, like network shape and topology. That was actually inferred for us, which is one of the interesting features of MxNet and Gluon. But we did have to write our own training loop. In the next video, we'll actually take what we learned here and then define and train an actual neural network in MxNet and Gluon.